Hello everyone, I'm Abhishek Kumar and I'm here to talk about my research paper Asymmetric in GAAS INP MOSFETs with source or drain engineering. My team members are Vishwanath, Karthik and Surya. Introduction. Asymmetric InGaAs MOSFETs are advanced semiconductor devices. They utilize indium gallium arsenide and indium phosphide materials. These MOSFETs overcome limitations of traditional symmetric MOSFETs. Source drain engineering techniques enhance carrier mobility and sub-threshold swing. They enable faster data processing and reduced energy consumption. Asymmetric MOSFETs are vital for high frequency electronics and low power devices. Ongoing research explores new possibilities for future advancements in semiconductor technology. Traditional MOSFETs and limitation. Role in modern electronics. MOSFETs serve as fundamental building blocks in various electronics applications, including computers, smartphones, amplifiers, and power converters. They play a crucial role in enabling digital logic, memory storage, and signal processing in integrated circuits. Limitations of symmetric MOSFETs. Power consumption. Traditional symmetric MOSFETs suffer from high power consumption during operation, especially in modern high performance devices. Performance challenges. As electronic devices become smaller and more powerful, symmetric MOSFETs encounter challenges related to speed, heat dissipation, and scalability. Leakage current. Symmetric MOSFETs exhibit significant leakage currents, leading to wastage of energy and affecting the performance of low power applications. Advantages of asymmetric MOSFETs. Motivation behind developing asymmetric MOSFETs. The motivation arises from limitations of traditional symmetric MOSFETs, which struggle to keep up with the increasing demand for faster and more energy efficient electronic devices. As electronic technology advances, there is a need for transistors with improved performance characteristics, particularly in terms of speed, power, efficiency, and scalability. Asymmetric MOSFETs with source or drain engineering offer a promising solution to address these limitations by introducing innovative design techniques that enhance device performance. Benefits of asymmetric MOSFETs over symmetric counterparts. Enhanced performance. Asymmetric MOSFETs exhibit superior carrier mobility and sub-threshold swing, leading to a faster data processing and reduced power consumption. Improved energy efficiency. By reducing leakage currents, these MOSFETs significantly enhance power efficiency, making them ideal for low power and energy conscious applications. High frequency operation. The unique design of asymmetric MOSFETs allow them to operate at high frequencies, making them suitable for high performance applications in communications and computing. Better scaling. Asymmetric MOSFETs provide improved scalability, enabling their integration into advanced semiconductor processes such as nanoscale technology. Potential applications and impact on electronic devices. High frequency electrons. Asymmetric MOSFETs find applications in high frequency circuits, including wireless communication devices and radar systems, where their enhanced performance can boost signal processing and data transmission. Low power devices. Due to their reduced power consumption and improved energy efficiency, asymmetric MOSFETs are well suited for battery operated devices such as smartphones, wearables, and IoT sensors. Specialized sensors. These MOSFETs are valuable in sensor applications where their low power and high frequency capabilities enable precise and fast data acquisition in various sensors technologies. High performance computing. Asymmetric MOSFETs contribute the development of more powerful and efficient processors, enabling faster computation and data processing in modern computing systems. InGaAs and InP materials. InGaAs, indium gallium arsenide. High electron mobility. InGaAs exhibits a higher electron mobility compared to the traditional silicon making. It's suitable for high-speed electronic devices. Direct band gap. It possesses a direct band gap which enables efficient light transmission and absorption, making it useful in optoelectric applications. Low indirect band gap leakage. InGaAs has lower indirect band gap leakage, contributing to a reduced power consumption in certain electronic devices. InP, indium phosphide. High electron mobility. Similar to InGaAs, InP also has high electron mobility, making it beneficial for high frequency and high speed applications. High electron saturation velocity. InP's high electron saturation velocity allows for faster electron movement, ideal for high power and high frequency devices. Optoelectric properties. InP has excellent optoelectronic properties, enabling its use in photodetectors, laser diodes, and other light emitting devices.
Source drain engineering techniques. There are four kinds of techniques: implementation doping, delta doping, selective epitaxy, strain engineering. Implementation doping, controlled ion implementation of dopants, selectively modifies the doping concentration in the force and drain regions. This process creates different carrier concentration, resulting in asymmetric and improved performance. Next, delta doping. Introducing delta doping, where a thin layer of dopants is deposited near the source and drain interface. This technique creates a higher concentration of carriers, leading to enhanced performance. Next, selective epitaxy. By using selective epitaxial growth, the source and drain regions are grown with different crystal orientation or doping profiles. This process allows for precise control of material properties, optimizing the device performance. Strain engineering. Applying strain to the channel region by introducing material with different lattice constants alter the band structure. Improving carrier mobility. Techniques like SAG stressors or strain introducing layers can be employed to achieve this effect. Next, fabrication process. Material integration. Combining InGaAs and InP materials introduce challenge in maintaining crystal quality and lattice matching, which can impact device performance. High mobility materials. Handling high mobility materials like InGaAs requires careful attention to avoid contamination and ensure high quality interface. Innovations. Novel source drain engineering techniques to enhance carrier mobility and reduce short channel effects. Improved gate stack materials and engineers for lower gate leakage and better gate control. Advanced device modeling and simulation to optimize device performance to predict behavior accurately. Performance matrices. First, current voltage IV characteristics. It helps understanding the MOSFET operational behavior and its region of operation. The sub-threshold region, where the drain current is exponentially small, is of particular interest for low power application. Next, transconduction. Transconduction is a measure of the change in drain current in response to change in gate source voltage. It represents the MOSFET's ability to amplify input signals and is crucial in analog and radio frequency applications. subthreshold behavior. In this region, the drain current is very small and exponentially depends on the gate source voltage. Subthreshold swing is a key metric that measures the change in VG required to produce a tenfold change in drain current. Low subthreshold swing in dedicate better switching efficiency and reduce power consumption.
Characteristics of an asymmetric in as AS/InP modified. First, A graph refers to the transconduction of versus gate source voltage. Shown transmission was InP and InGaAs as drains. Transconduction is the change of drain current devised by the characteristic of gate source voltage. Transconduction include whether the increases of data source voltage from both InP and InGaAs as drains. And the G graph B refers towards transconduction versus drain source voltage. Installation of transconductions from the InGaAs as drains. Transconductions devise whether the including of drain source voltage and common characteristics of modification. And the graph C refers to the frequency versus gate source voltage. Shown frequency from the InP and InGaAs drain. Frequency including the increasing of gate source voltage and both InP and InGaAs as drains. Increase the operating free radius on modification at the difference gate source voltage level. The graph D refers to the drain current versus drain source voltage. Isolated the operation characteristics of modified from the InP and InGaAs as drains. Shown how the drain current change whether the variable drive source voltage from the given gate source voltage. Drain source increase the increasing of drain source voltage to the InP and InGaAs source drain. This graph's collection provides the various insulation into the meaning of preferences of asymmetric InGaAs/InP modification help reference to and energy operation of device to the utility to effect of variable electrical applications. There are three applications: high frequency electricity, low power device, specialized sensor. High frequency is asymmetric modification whether the enhanced current modification or will be suitable for high frequency emission. These find the high speed continuity systems, radios and wireless transmission whether the first data prefers the n sign application and characteristics. The low power drives that electric to the low located current and make the asymmetric modification ideal from low power electricity. These are the suitable for prevents the drive like symmetrical table and wearable whether the energy efficiency in circle for executing battery lives. Specified sensor asymmetric modification can be enabled in specified sensors such as GAAS contains binary in image source sensors. These enables to operate at high frequency and low power consumptions can be changed sensor sensible and requirement. Analog and radio frequency applications. The high transconduction is application modifier and make them variable of analog current and RF applications. They play significant roles in significant efficient applications. Finish to arrive the system RF amplifier and radio frequency including the RFD drive. High performance computing. The asymmetric modification adult to operate at high frequency and handle large data load, make them easier communication to the in high performance computing systems. These contains the fast data preference and complete in super complicated and data contains photo photometric and operating photometric and operating electronic system. Asymmetric modification can be including whether the photometric contains of form of operation device. These drive varying method of likes enhancers enable efficient light emitting the delivery of making the voltage of operation communication in image drives. Special and specific technology. In space applications, whether the efficiency and radio technology or crashful asymmetric modification can be preventing radio frequency in extruding environment. Power Power electronic asymmetric modification can be enabled in power convolution and involving for efficient energy converting and power modification. Asymmetric InP modification offer the wide range of application occurrence in different field, creating to the growth of driving factors, energy efficiency and high performance electric drive. These various and unique characteristics make them prevention contains from future applications in symmetric technology. And the last thing is conclusions. There are asymmetric modification add that limited of increasing systematic modification applications, increase the performance, reduce power communication and enable to scale. And the energy technology like implement both developing boards and selective equation of creating asymmetric in the source and drain region of drive preference. The key performance methods such as transductions, subtrending drives and carrier voltage characteristics helps and characterize operation the beginning of asymmetric modification. Analytic modification like the EVG and ACM for enhanced modification and equation creations mode of preference drive to do the caloric drive implementation. And the last thing is asymmetric modification finally applies to the high frequency electricity, low power density, specified sensor, analog and RF circuit, high frequency combination